And let's look at the test. The very least, the synthesis one is probably one you want to go over.
Yeah.
Should we run through mechanism or the reactions real quick? All right. Alkene, HBr, acid catalyzed hydrogenation, Markovnikov. So we're getting 1, 2, 3, 4, 5. Plus En. Is there an R plus S in there?
You could go like front or back.
Yeah, its shape is actually gonna look like that, but is that gonna is the mirror image of this as the molecule? No, because the ethyl groups are identical. So just one equivalent of chlorine here. No HB or no light, so it's not the radical catalyzed. So it's just gonna add. We're just gonna chlorinate both sides to 5 bonds. So 1, 2, 3, 4. Bromine with water. So we're going to make that bromonium the 3-sided ring as the intermediate, and then water as our nucleophile. So we're going to make a halohydrin. The bromine is going to go in the less substituted carbon. And it's going to go in the opposite direction as the OH. So that one is going to have a plus En.
Does it also have you could put the switch the VR and the OH?
No. Because we make that 3-sided ring, when we do those ring opening reactions, we always open on the side that's more substituted. So the OH has to go on the one that has the metal. If you drew all 4 possible stereoisomers, though, that's still a 3 or 4. Because you got the right reaction, you just mess up the stereochemistry. Lindlar's catalyst does what? And 1 equivalent of hydrogen. That's your other clue. 1 equivalent of hydrogen means we're going to partially hydrogenate. And Lindlar gives us the cis or trans.
Cis.
You gotta do the
Yeah. Cis.
So we get the cis. So 1. So we're gonna get that molecule. Excess NaNH2. So we're going to make the alkyne with a double elimination and then deprotonate the terminal alkynes. The intermediate looks like this, which is then going to come in and attack here. So we're going to add that's where we started. We're adding 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. As usual, trickiest thing with these is make sure you didn't add or lose a carbon somewhere. So with the cheat sheet, the reaction shouldn't have been too bad, right?
Yeah.
This is all feeling pretty good.
Yeah.
Remember that reactions was 40% of the test. You want to do the other page of reactions? All right, we're already here. Let's do it. So, hydration, hydration, anti-Markov. It's an alkene, so we're going to make an alcohol. We put the OH on the less substituted carbon, so on carbon 2. We have to worry about stereochemistry.
Oh, but we made a chiral carbon.
We made 2 chiral carbons actually. So this is one of the ones where full credit is going to be a much bigger reach than 3 out of 4. Because you have to remember that the oxygen gets added on the same side boron is on. So if the boron is coming up, the oxygen is going to get added. So the boron adds here. The oxygen is going to be on the same side as the boron, which should be the opposite side from the methyl group. So if the methyl group is down, OH is up, plus the N. Right, so it has to be syn addition, which means the anti product. All right. Mercury, acid, alkyne, hydration, Markovnikov. So 1, 2, 3, 4. Right, we start by making the enol and then rearrange. This one's going to look funky, but it's not actually that bad because all we're really doing is cutting right there, right? Which means what we're left with is a cyclopentane. And then right, because they have to be cis relative to each other because they started cis relative to each other from the point of view of that cyclopentane. And yes, in light as what?
It's been a week and I forgot. But
Radical. And the NDS keeps our concentration of the bromine low, so we predominantly get the bromine only being added in the most favorable spot, which is in the allylic position.
But we,
But, go ahead.
it's symmetrical, so I mean, I guess 2 positions that it could be in.
So if we ignore resonance,
Yeah.
which we don't usually do, we're gonna put it there. Okay. And all of the methyl groups are identical. However, we're gonna have a resonance structure that looks like this, which has a resonance structure that looks like that. That one's more stable. So we're actually gonna put the bromine. The full credit answer, another one where 3 out of 4 was pretty easy to get into 4 out of 4. That required one extra step. We're gonna put the bromine there. But at least there's no stereochemistry because we have 2 identical metals attached.
Yeah.
This is one of the reasons why I don't do multiple choice for reactions and things like that, because I'm really testing you on like 3 levels of things.
I feel like multiple choice would be great.
Yes, but believe it or not, there are standardized tests that for chemistry, MCAT,
Yeah.
whatever the vet equivalent is, the dental, is that TDAP or something? No, TAT. TDAP is that shot, right?
I think so, yeah.
But there's also the GRE for chemistry, which is the grad school test for people going into chemistry for grad school. And so it's a standardized test set up like an SAT where you have to do, it's basically on all 4 years of your chemistry degree. All at once. So multiple choice questions do happen, but they typically ask them in levels. So you have like 100 instead of only having 10 reactions, you have like 100 of them. Some of them are the simple ones, and some of them are the more complicated ones. All right. This one, we get a little bit of everything, right? We're gonna get that. And that one doesn't have R plus S.
It's symmetrical.
Because it's symmetrical, because the 2 ethyl groups are the same. All right, now that we've done the ones that you felt pretty good about already, let's talk about the mechanisms. We won't go through them in exhaustive detail, but one thing that I will say about practice tests and study guides in general, if I give you a practice test that has certain mechanisms on it, that doesn't mean those are the only mechanisms I'm going to ask about.
Right.
In fact, you can usually infer that if I put these mechanisms, if you have 6 mechanisms and 3 of them are on the practice test, odds are pretty good that the other 3 are going to show up on the test. All right, so for this one, our Rocco, we had that weird 5-sided intermediate. We're going to start by making the epoxide. So the trick here was remembering that our other way. This is the one where we get that weird 3-sided intermediate, where we wind up with a lone pair grabs a hydrogen. Those electrons move over. Those electrons move up. So we wind up kicking an oxygen out. Because this one's gonna reform into a carbonyl, this is gonna turn into an OH, this oxygen gets turned into the epoxide. So we get an intermediate then that looks like this. And then if it's acid catalyzed ring opening, acid catalyzed means the first thing you do is you find the lone pair, you find an extra pair of electrons somewhere. Either a lone pair or it's 5 bonds. And you protonate it. That's now not super stable. So now our water comes in here. Does the SN2 attack.
Careful.
It's closer to that than I thought it was, obviously. So SN2 means that stereochemistry flips. So I'm actually showing this for the opposite of the one that was here. But it's the same step. If I was being really careful, I would have just started by doing it. That way. Now it'll match the right stereochemistry in our final product. So that gets us our anti-addition. So now our methyl group is down. We get an oxygen with 3 bonds facing up. OH on this side. All right, then a quick proton transfer and we're home. So our last proton transfers, that would just be something like that.
Is the O in that other red on the top, is that on the,
That one?
is that on the rubber in the base of the ground?
It's coming out of the board now because it did an SN2 reaction, so I flipped the stereochemistry here. This leaving group leaves, so this oxygen is still facing down over here, but this methyl group that was up, remember, does that umbrella flip.
Yes.
So that doesn't matter as long as the in and out are roughly in the same direction. Because really what we're trying to indicate is that they're on top, right? And also, just more good test taking strategy. This was a big lift here, right? This was the trickiest part. If you can't come up with that on the test, but you know that you're gonna come up with this, you can hand wave this. It won't be full credit.
Right.
But if you can say, okay, I forget how to draw it or give it your best try, but at least get to this. And then do the rest of it forward, because if you got from here forward, that's at least 6 out of 10. And if you gave this a decent try, then I can give you a point or two for that. The main thing is don't let not knowing an early step derail the whole thing. Right? That's one of the big keys about having these landmarks along the way. We watched way too many Olympics during our snow days. We watched so much curling. Yeah. My kids really love curling, probably because Bruce and his son Matthew love curling. So my kids have now adopted it as.
Talked about the Olympics since the school year started, or since his quarter started.
When he's getting ready to this year, he was not pleased to have these snow days because he's going to be gone for the World Baseball Classic. But the other nice thing, the fun thing about curling this year is there's drama.
There's drama.
There's drama.
What's the drama? I'm not clear.
The Canadian team keeps double tapping the stone. They let go of it and then they touch it one more time. Yeah.
But is it cheating? I thought they got.
It is.
But they're not doing anything about it?
But they didn't get called on it the first time. They get called on the second time. But then the guy who did it the first time said, "This is ruining the culture of curling. This is a gentleman's game. We're just supposed to take each other at our word. You're not supposed to actually call me on breaking the rules."
Right. It's not like you're in the Olympics or anything.
Right. I don't know who goes to the Olympics and expects to not have to follow the rules, but. Oh, it's fascinating. I love good sports drama. All right.
Well, and there's like everyone's like, the ice is bad. I've heard that the ice is really bad because they're using the same ice for speed skating and they're like, girl, it's not the big temperature, it's too slushy. Yeah, it's too warm for you to be done. I'm like,
Yeah. I did hear something about that. They have double Zambonis going, so I feel like they could get that ice nice and flat.
it's like we off monitoring the temperature, like the ice is fine. I don't know, everybody has a phone.
It's true. It's true. But clearly not everybody. People are finishing races, but the Americans are falling
I guess.
in the speed skating anyway. All right. Ruhr. So for free radical reaction. This is one of the ones.
I was doing it and at one point I was just like, you know what, I'm just going
That's fine. You get to the point where like, okay, I'm not getting more points here. If you're spending more time on it, then it's worth it. You should cut your losses, move on. So anti-Markovnikov HBr edition. So our initiation is actually going to be splitting up the peroxide. So it looks something like that. So we'll get 2 oxygen radicals. The oxygen radicals, so technically we usually, because it's not going to add up to our overall reaction, our next step, we actually have 2 initiation steps for this one.
Okay.
Because even though it's technically looks like a propagation step, we're going to draw it like this. The more stable radical is going to be on the tertiary carbon here. Sorry, I take that back. We don't have it attacking this first, it attacks the HBr. Because we're not adding oxygen. Alright, so how do we know which one of these gets to stay as a radical? Well, because I kind of worked backwards from this. If I'm doing this off the top of my head, and I wouldn't necessarily, if you have a page of notes too, I wouldn't necessarily expect you to take this logic. But the way that I can tell that we're gonna wind up with the bromine radical instead of a hydrogen radical when we do this is because my final product is gonna put the bromine on the less substituted carbon. So I know that my bromine radical has to be the next thing to attack, because I know I'm gonna make an intermediate that puts the radical right there. So because the bromine has to add there, I know that the bromine radical has to be what I make it here. Because then we can say, okay, bromine radical plus this.
Only one plus. What are you problems that don't work? That's everything that don't work. So it's not a propagation.
So this is propagation, yes. Yep. Because we know that even though this is technically a propagation step, because we end with the same number of radicals we started with, we know that this is not going to show up in our final product. And neither is this ROH. It's not showing up as our final product. So it's not going to be part of the reactions that we sum up for propagation steps. And for the termination step for this one, this is the one where we said don't worry about which ones specifically running into each other. Just pick any two radicals that you drew.
Right.
And draw them counteracting each other. Right, but these are the four important steps, and then termination, as long as you show me something, could even just be bromine radical plus bromine radical. To make Br2 would be fine. Okay.
Termination or elimination?
Termination. All right, I'm gonna go to the left side.
You only have one termination step.
We'll always have one termination step. You can pick any of them to draw, but you only need to show one termination step. So just pick, in this case, any two radicals that we drew and show them running. Alright, so this is a long one. It's not particularly, it wasn't too bad, right?
This one didn't feel. So it was basically just take the lowest going and the ones.
Yeah. So. This is gonna grab a hydrogen. Bromine leaves. The carbon hydrogen bond turns into a bond. And then we're here. And we're gonna do it again. However, that doesn't, just ending there doesn't explain what the water's doing. That's the 8 out of 10 answer. The 10 out of 10 answer, you actually, even though the steps are gonna add up to canceling each other out, we still would want to show. We're gonna deprotonate terminal alkyne, and then step 2 is add water, which is just putting the proton back on. Like I said, the last 2 steps really do just counteract each other. But it's what actually happens in this mechanism. So, but if you just stop there, it's an easy 8 out of 10. Okay. So we added excess of the amide at the beginning because we wanted to make sure that we pushed the usually all the way to completion, right?
Right.
But the side effect of that is that it does this. If you add enough sodium amide to be sure that you make all of the alkyne possible, you also have to add enough of the amide that you're going to deprotonate it. So you can't really just say, I'm going to add 2 equivalents of these, because then we wind up in an equilibrium situation, we don't get as good of a yield. So we add the excess amide, and then we come back and add water, basically to counteract whatever this is left. And then also put that hydrogen back on. From a theory point of view, these last two steps are redundant. It's from a practical point of view, though, you can't just ignore them.
Right. These stories.
All right, and just also a note about grade. I already told you that getting those first two steps is 8 out of 10 here. For the radical one, as long as you recognize it was a radical reaction and try to do initiation, propagation, termination, I can give you 4 out of 10, even if they're all totally garbage. As long as you tell me I know that this is radical, I can give partial credit, right? So, especially not on my tests.
Yeah. Most teachers, at least here,
Mm-hmm.
if you teach something, they'll give you a point.
We don't like to give zeros.
Right.
So you'll give us something.
It's like, sometimes it's synthesizing it. You got to pick your journey.
It's true. It's exactly what we're gonna do. And you just throw water in there whenever you need water.
It's a very easy resource. I did. There was a point on the test, I thought the negative on the O was like a mark and I was trying to erase it. I was like, what is happening? And I go, oh, that's
okay.
it.
So if we know that these are our resources, the way that I would approach this would have been to say, okay, well, that's a toluene. The hint tells you we're adding this at the very end.
Yeah.
So that's an acetylene. So I need to find a way to attach an acetylene to a toluene. And then I need to find something, if the acetate is going to act as a nucleophile, I need to have a good leaving group here.
Right.
Right, so if I'm just working backwards, one carbon, 2 carbon, 3 carbon. I know I can do this because the hint says acetate can act as a nucleophile. So as long as I have a good leaving group where I want the acetate to be attached, we're good to go.
Sure.
So then how do we get here? Well, remember that these 2 carbons, I'm pretty sure are coming from an acetylene. If they're coming from an acetylene, that means that there was an intermediate that looked like don't lose a carbon anywhere. I'm still not filling in all the steps yet because now I need to be able to go from here to there. But I know how I can add a bromine there. If I do a partial hydrogenation, then I would get to this. I can get here, right? And then I can just do HBr, Ruhr. So then how did I add an alkyne on here in the first place then?
Well, the example that it gave us was like. So like. We would have just added. It was. Would have had to.
So we need a way to attach the acetylene. We're pretty sure that this came from acetylene, right? And this is toluene. So we can have acetylene act as a nucleophile. We just deprotonate it, done that once, right? You just need a good leading grip on it. Or you can write it above that. So you protonate your acetylene. Then the last piece is how do we brominate the benzoic position on toluene? We only have one reaction that does that. And it was one of the mechanisms we just looked at. We did it in the allylic position. Actually, I think that's not one of the mechanisms, it's one of the reactions.
Yeah.
All right, and again, when I'm grading these, I'm looking for, did you hit some of these landmarks, or is the path that you came up with equally valid? If you came up with a different, completely different path that still gets you to the right molecule, then there might be some points off if it goes a very like circuitous route, but I can still give you most of the points. Fun fact, this is actually exactly how they make artificial, some of the components of artificial cinnamon flavoring. So if you start from cinnamon aldehyde, the one we played around with in lab, is the one that you just want essence of cinnamon. That's what you go with. But if you want a more well-rounded flavor, then you make these other compounds as well. So it'd be still synthetic, but more well-rounded tasting cinnamon extract is going to have this compound in it. I thought we're supposed to stop snow today. It's gambling out there. I hate when I have to leave the house when it's snowing because I know when I get home, I get to clear the driveway before I can park the car.
Yeah. We on.
You're in Christmas Valley, right?
Yeah, on Tuesday, all of us, Mikey together, me, mom, and dad, we're all. And that's technically. We have snow twice. We have to do it in the morning and then at like 3, we had to go back out because they like doubled.
Yeah, it was bad. Tuesday was I think we cleared snow 3 times on Tuesday. And that included our next door neighbor's house because she doesn't have a snow blower and she watches our cats for us. So we do a lot of things for Ayana because she helps us a lot.
Yeah.
But
That's
it was a
like,
lot.
yeah, it's like, put like a trash bag over his gas. What are you doing? Like, I know how to use the snowboard, like, go back to inside. Like, you put like outdoor foot thing, and like, it has to action. And then find like, oh my gosh, like he sent pictures of this. Like, is this guy like crippled right now and still snowboarding? And yes, so I was like, yeah, we can't make him stop.
That's
We tried to chug out, me and Mike went to have a neighbor in the evening, who had their trucks in the street. And Dad tries, gets like halfway, and he's like, this is too deep for me, and my leg, I think I'm going back, and I was like, I told you to stay up.
yeah, but he felt like he helped though. That's what's important.
I mean, you can still snow those. Whatever works again.
I could see you snowballing because they're heavy enough that you can hop on it and lean on it pretty well.
Well, and he has his peg, which he like works really well.
So is he doing one of these? Yeah. Okay. Yeah, I've seen those.
But then he was able to see it actually.
All right. So this is the one I actually. Oh. Sorry, I tried to scroll, forgetting I'd started the slides. All right. Let's take a break.
Okay.
We just started the slides, but that's okay because these slides are going to go fast because really we're just talking about acid bases and alcohols. So we'll come back at 11 and we'll talk about alcohols. Start the next chapter.
All right. What did you say? I was. Well, I sent it first. It's up at 4 a.m. You have the next one you wakes up at 4? No. How to get to work and like takes 2 seconds. My phone would go off. The first thing I don't want to have. Yeah, there's no one there.
Because everybody else looked at the weather and,
Is there dead comes with?
I mean, on the books, I don't know what Carl's got going on in his personal life. I just don't want to get a whole lecture behind with you all. Otherwise, I would have canceled class today. We could have. Right. So besides, if we were doing it remotely, I'd have all three of my kids at home with me, which doesn't always lead to the most cohesive lectures. We're trying something new today. Dash is 12 now, so he's now legally able to babysit his siblings. He's in charge. The other two are 6, so.
So then it'll be easy.
Dash. He's much better though. It should be easy. Yeah, all he's got to do is give them food every once in a while.
Fine.
He's mostly, he turned a corner on Saturday, so that helps. But yeah, last week he was the one who was down for the count.
Right.
This week it's his siblings. We watched The Thing with them on Tuesday. The Thing. It's one of the best horror movies of all time.
But tell me about
It's Kurt Russell in as a helicopter pilot for a research facility in Antarctica.
Okay.
And the less you know about the plot line, the better, the more fun it is.
Well, maybe I will.
It's like I don't go for just horror for the sake of horror movies. It is a good movie that happens to be a horror movie.
Is there something out in the Arctic?
So that's why we watched it on Tuesday when it was blizzarding.
Scaring children?
They begged to watch a scary movie.
Really?
And we finally hit Kuiper's limit. The 3-year-old, he watched Walking Dead with us. And so he loves zombies. He loves scary movies. He reached his limit with this one. Was like, I don't want to watch this one anymore. And this is the first time he's done that. So.
California. And it's
Okay.
a creature that lives in the fog and the sky lives in the light. And I haven't seen it yet, but because I'm too scared. Because I love fog. I love fog so much. I'm like, I don't want to ruin that fog for me.
Well, similarly, this one takes place back east, but there's The Mist,
Okay.
which is a Stephen King book that got adapted. I believe it got good reviews though. Stephen King's real hit or miss when it comes to the movie adaptations, but I think The Mist was supposed to be pretty good. But anyway. All right, since we're all here, let's get through some slides. All right, so we're going to talk about alcohols now. We've been making alcohols by using hydration reactions of alkenes. So we've been dealing with them a little bit. We haven't learned officially how to name them yet. It's really easy. You name the molecule like normal, and you drop the E off the end. And you put OL. So ethane becomes ethanol. And cyclopentane becomes cyclopentanol. So we're still looking for the longest continuous carbon chain that has the functional group. This is our suffix though now. So ethane, drop the E, put OL. Obviously alcohols show up in a lot of places in nature. Phenol is a really common molecule. You use this in medical settings to disinfect, where you don't want to use iodine necessarily to disinfect. Phenol gets used fairly often. I want to say like something like hand sanitizer. It's not just straight isopropyl alcohol or ethanol. It's some version of a phenol. And just a note about the pronunciation, we overemphasize the OL part here because phenol is different. Phenyl means you've got a benzene ring as a branch. Phenol means that you've got an OH attached to a benzene ring. Both of which are spelled differently than the herb phenyl, which has no phenol in it. So just to keep that in mind.
Language class should be a subject built around.
It does kind of help to have some amount of it be systematic. Not every alcohol you see in biological applications ends in OL, but most of them do. So capsaicin is a phenol. It just has a bunch of other stuff attached to it as well. You do watch Hot Ones?
The hot sauce thing? Yeah.
This is where they get Scoville units. It's basically from the capsaicin count. So the Scoville units.
That's huge.
Yeah. So it's in a mine. It's not that big by biological standards, it's big by organic standards.
Yeah.
But yeah, that's what makes things taste spicy. And I believe that that's the primary component in. No, I take it back. Capsaicin is not in pepper spray.
Okay.
Pepper spray is a different compound called mace
Right.
that we talked about last quarter.
Is this naturally occurring?
Yeah.
Like chilies and stuff?
Yep. And basically what it does to make things feel hot is it binds to the proteins in your mouth that are responsible for detecting heat. And it changes their 3D structure in a way so that they actually send positives saying it's hot at a lower threshold. So basically like lowers the threshold for your mouth to consider itself hot. So your mouth, even though your mouth is not physically any hotter when you eat something spicy, you start sweating because it's basically the heat your body in your mouth is now enough to trigger that signal saying, hey, it's really hot. So and interestingly, menthol does the exact same thing, but for the cold enzymes. The receptors that detect cold get modified by compounds like menthol to trigger a false positive at a higher than normal temperature.
Like it's kind of like mixed baby club. Is that like what's in it to make it?
Yeah, right. And that's why it feels cool, even though your temperature didn't change. But if you've ever tried drinking like room temperature water after you brush your teeth, it feels like ice water, right? And that's just because you're getting those false positives sent to your brain because there's a molecule, menthol is smaller than this, but basically it's just gumming things up and accidentally triggering these false positives, not accidentally, but then a lot of them will also end in OL. If you see something ends in OL, almost guaranteed it's an alcohol. This obviously THC has a lot of other stuff going on as well. But it's named as an OL, as an alcohol. So even though capsaicin is not named as an alcohol, that probably tells us that that was like one of the last functional groups they figured out. They knew what it was as a molecule before they knew what the structure was. Right, so naming these. Longest continuous carbon chain with the alcohol. Count it out. And then add any substituents, any prebases that you need. So any branches, halogens, anything like that. Right, so really all we added was this new suffix, OL.
Yeah.
We put in the work to learn how to name things properly. So it's not that hard to add another.
So, but we still don't want to count like in and out of rings.
Correct.
Right? So if we can have like a machine, we're still only gonna count the ring.
One, two, three, four, five, six, seven. So. This we're gonna name as cyclopentanol with the big long branch.
Okay.
So this would be, if we're naming this big long branch, it's 1, 2, 3, 4, 5, 6 with a methyl. So we're gonna use parentheses. So it's gonna be 1 methyl hexyl. Methyl hexyl. Cyclopentanol.
Okay.
And we don't need to specify where the OH is because it's a cyclo group. So just like with alkenes, alkynes, we assume that that's carbon 1. Which would mean this goes on, it'd be on carbon 2. And this is also where you start seeing them put the 3 in the middle. It would not be uncommon for this to be labeled as known and 3-ol. I don't like that, but that's where you would put it. It's right before the OL part. You can tell I don't use that picture very often because I had to stop and think about where you would put the 3. You put it in the middle.
Yeah.
It's always right before the tag for the functional group.
Because we've seen that before.
Yeah, with alkenes especially. The one place where you would definitely need it is if you had a molecule that has more than one functional group. So because this is an alkene and an alcohol, so we would say that it's going to be 1, 2, 3, 4. So it's butene. One all. So 3 butane, 1 all. We would always put the OH, whatever you say at the very end, is highest priority for the numbers. So because we're going to end with OL, it has to be carbon 1, which means the alkene is carbon 3.
But we don't do ENE because of the OL.
If you did that, nobody's going to think twice about it.
That's probably.
Yeah, I don't think that's wrong by any stretch.
Okay.
I learned putting the numbers in the middle as a last stitch, so there's less of an emphasis on the spelling for those.
Okay.
So when you have 2 functional groups on the same molecule, especially if you can't name one of them with a prefix, then putting the numbers in the middle is almost unimportant. And just because I occasionally run into chemistry meetings,
I think water is an alcohol.
organic chemists don't particularly like that approach because you need a carbon for the OH to be attached to, but you're far from the only person to think that.
Okay.
All right, let's talk a little bit about properties. Alcohols are interesting in that they can make hydrogen bonds similar to water. So they're not fully non-polar molecules. In general, when we have these molecules that have this very strong polar group as part of that molecule, in organic chemistry, that typically means we're gonna have a hydrophobic region and a hydrophilic region. So when it's a molecule as small as methanol, you don't really notice it too much, but basically, the bigger this aliphatic region gets, the less soluble it's gonna be in water. But because we have a larger hydrophobic region, but still just have the same size hydrophilic region. Right?
Larger, they're less soluble.
Correct. And so there becomes a point where there's sort of a trade-off. When they're small molecules, we say that they're soluble in water, we use the term miscible. You remember us using that term? Miscible means that there's no limit to the solubility. Basically, you can add methanol to water, and it's not saturated ever. Because what eventually happens is instead of it being methanol dissolved in water, eventually it turns into water dissolved in methanol. And so there's no practical limit for how much methanol you can put in water. You can put it in any ratio you can call it. And ethanol behaves the same way. But then when you get to these larger molecules, the solubility starts dropping. And so typically, we still consider it soluble in water as long as there's no more than 5 carbons for every OH group. They're not fully miscible once you get larger than a 3-carbon OH group. You wind up having some limits to the solubility, but they still dissolve pretty well until you get to something, say, this large. So like cyclohexanol doesn't dissolve in water. Again, it mixes just a tiny bit. For the most part, we can say it's insoluble because it will actually form 2 layers. But methanol will never form 2 layers with water. Ethanol will never form 2 layers with water. I want to say isopropyl alcohol. It's really close to being truly miscible, but there is a limit where you can get to the point where isopropyl alcohol will form 2 layers. But then if we start adding more and more OHs onto that molecule, that sort of resets. So the rule of thumb is 5 carbons per OH group is the limit of solubility. So even though like glucose is 6 carbons, but it's also got 6 OH groups. So glucose dissolves really well in water because even though it's got a lot of carbons in it, it's not really, it's not rising to that ratio. It does still have a limit, it's not truly miscible. But basically that's what we're looking at when we're determining whether or not something will dissolve in water. So we're looking at that ratio. The most common place we see alcohols is in sanitizing mix. Because they have these antimicrobial properties, basically because we can add alcohols in large amounts and it changes the polarity of the water. It actually it kind of gets in the way and gums things up for cells. So it basically kills the cells by changing the solubility, which changes how proteins fold. And if the proteins can't stay folded properly, if they start getting denatured, then that's going to basically render that cell totally dead. And viruses too, for that matter.
So when people like die from alcoholism, is it because the alcohol breaks down their proteins?
No, but it does do that, but our body's pretty good at handling ethanol. there's a lot of other things that go into it. Basically, like the liver's primary job is to filter toxins out of your bloodstream from your digestive tract. And so people that chronically expose their liver to excess alcohol make the liver work harder than it's supposed to, and that can actually cause scarring on the liver. And basically your liver stops working because you just worked it too hard for too long. Obviously single-celled microbes and viruses don't have that issue because they don't have livers. If there was, so the way that alcohol works in the human body is just going to be a little bit different than with microbes. But basically, it's one of the reasons that we use alcohol, and especially ethanol, that our body can tolerate, is because it breaks these things down and preserves things without necessarily, but still leaves it so that humans can eat it. So it's similar, actually, the same process that we get when we cook something. When we cook something, we're just denaturing the protein so that they don't work anymore once they get into our body, right? We can do that with pH. You cook something in acid, like a ceviche or something, that's never been exposed to heat, but it's still denatured pathogens. And so alcohol can do that too, as can salt. That's why you salt things to preserve them, but you can also just put them into alcohol. If you put, I'm trying to think of what the traditional, like vanilla extract, it's a really common example. Nothing's going to grow in vanilla extract because it's just like Everclear with that you soak vanilla beans in.
Yeah. That's much yummy.
It's much yummier. Although I don't know, have you ever tried taking a shot of vanilla extract? Not only is it not cost effective, but it's way too strong.
When I was a kid, because I was like, it smells so good, it must taste good. So my dad was like, try some. I was like, hey, it's yummy when you don't play with it. Yeah. But it's yummier in stuff. Yes, agreed.
What we do see though is that once you get large enough molecules, large enough alcohols, that antimicrobial property kind of disappears a little bit, because basically there's so many alcohols that are present all the time, like not phenylalanine. There's several alcohols that are essential amino acids that our bodies, all living things, need to build their proteins. So obviously that wouldn't work very well if they were also toxic. So our body has ways of handling larger alcohols just fine. It's the smaller alcohols that are toxic to us and other microbes. So here are two other ones that get used in I think resorcinol gets used a lot in like wipe on disinfectant things. I believe it's the one that's like yellowish. If you've ever seen like on a surgery where they wipe down the area with like this yellow, I believe that's resorcinol. Because it doesn't evaporate so fast. When all you're doing is giving someone a quick jab, you don't necessarily need it to stick around a long time. So you just use ethanol and then it evaporates off really fast. If you want it to stay sanitized for a while, then you use these larger molecules just because they don't evaporate as fast. All right. Big topic for today is acidity of alcohols. How do we know how acidic different compounds are? We've been using these different acids for a while now. We have a pKa chart, but if we don't have the pKa chart sitting right in front of us, how do we determine what's going to be the most stable or what most acidic protons? And in general, things that are further to the right on the periodic table are going to be more stable when they're deprotonated. So a carbon is less stable when it's deprotonated than nitrogen. Nitrogen is less stable when it's deprotonated than oxygen, which is less stable than a halogen.
So the right is more stable.
The right is more stable. Right, and so we did have a pKa table, we see pKa of just carbon hydrogens, alkanes, is between 45 and 50, so super high. Amines is between 35 and 40. Alcohols between 15 and 18, and pKa of halogens is between -10 and 3. So even fluorine, that's a weak acid, is still way more acidic than any of these others. Right, and go along with the water is really an alcohol. Water's pKa, it's right in here too, right? It's right around 15. So if we wanted to deprotonate alcohols, so let's say we wanted to use sodium ethoxide. Let's say we want to make this that we can use as a nucleophile for something. If we want to deprotonate alcohols, we can use sodium iodide, but we don't get great yields. Why might that be the case?
Is it not gonna attack everything?
It's not going to attack super well, and we're going to make something that is also a weak acid then too. So even though this NaNH2 has a very strong pKa, it's very basic, we're still going to wind up being limited by equilibrium. Whereas if we use something like sodium hydride, or even just sodium metal, in both of these cases, we make hydrogen gas as one of the products. If we make hydrogen gas, that's no longer part of the equilibrium process, right? Because it's not in solution anymore. What this symbol means is that it leaves the system because it's a gas. So if you make something that's a gas that can then be removed, then it's not going to affect our equilibrium at all. And that gives us a better yield. So we can do this with pretty much any alcohol. If we take any alcohol and expose it to either sodium hydride or sodium metal, we're going to wind up deprotonating it and making something that is actually stable enough we can isolate it. So just like sodium hydroxide, we can isolate it as a solid. We can isolate sodium ethoxide as a solid as well. If we try to do the same thing when we had when we did it this way, we're going to get NH3 plus our deprotonated form. Well, what if we try to evaporate off the water or try to evaporate off the solvent? When we do this, it's actually going to be pushed. It's going to wind up going back this way because sodium amide is more stable as a solid. So basically, we don't see that. We can use sodium amide, but we don't generally do that for practical reasons. All right, let's talk about phenols. Phenols have much lower pKa than alcohols. Similarly sized alcohol to a phenol has a pKa of 18. Cyclohexanol pKa of 18 compared to 10. That means a factor of 10 to the 8 times more acidic. What's one reason why that might be the case? And so what do the double bonds get us? Fewer hydrogens.
Well, but more than the other, right?
This one's gonna have.
Oh, wait, no, yeah, never mind, never mind. And that's one of our bases.
No, what, Taylor, what makes the double ones? That's one.
More electrons, and
Yeah.
more electrons means what? What else can you do with it? You can steal them. What would it look like if we deprotonated this? When you have a charge adjacent to a pi bond, what can you do? You rearrange it. We call that what? It's not a rearrangement because this is the one that happens all simultaneously. That's what type of arrow?
No.
Say that louder, Taylor. Nope, not an isomer. I thought you said the right word. It's resonance. Right, so if you deprotonate a phenol, you get a negative charge on that oxygen, which can then resonate all around that ring. We get three different resonance structures. And remember, resonance makes things more stable.
Yeah.
Because you can spread that negative charge out. All right, so here's the other, so resonance is one of the most important things when it comes to guessing, not guessing, but reasoning your way through what's more acidic. If you're making something that can be resonance stabilized, that's gonna make it easier to pull off that hydrogen. So basically, when we look at these, we're always gonna look at these in terms of how stable is the product. It's a lot more stable to deprotonate this because you get that resonance. There's no resonance here.
Right.
So it's less about how stable they are right now and more about how stable is it once we deprotonate it. So these other ones are not specific to phenols versus regular alcohols. But if you have a bunch of electron withdrawing groups, if you have something nearby that can pull the electron density away from that oxygen, the electron density is what's holding that hydrogen on in the first place, right? Because basically you've got this, all this electron density that your hydrogen, your H plus, is basically just like stuck to one of these clouds of electrons. Right? And so if you can pull the electron density this way, that's going to make that hydrogen a lot easier to pull off. It's not stuck there as strongly. And so we call that induction. When you just stick something electronegative and it's not resonance, it's just basically pulling through the sigma bonds. We call that induction. So the more electron withdrawing groups you have nearby, the more acidic your alcohol is going to be. All right, there's one more way that we can stabilize these products, these deprotonated alcohols. It's not necessarily one that you would guess. So I'm not going to make you guess. Solvent. Solvent, back when we talked about SN1 versus SN2, we talked about how solvent molecules can stabilize nucleophiles, right? With protic solvents, we basically could make our nucleophiles less nucleophilic by surrounding them with so, with positive charges from the solvent molecules. So the more that you can, stabilize your product with solvent molecules, the more acidic it's going to be. So ethoxide is more acidic than t-butoxide. Or sorry, ethanol is more acidic than butanol because of the sterics. Ethoxide, you can get a whole bunch of solvent molecules around it to sort of stabilize that negative charge. And if we're talking about water molecules, then they're just going to be all arranged so that we get the partial positives from the hydrogens are going to be pointed towards this negative charge. That makes it a lot more stable, right? But the more sterics we have around, the less room there is for the solvent molecules to come in there. So smaller molecules, primary alcohols, tends to be more acidic than tertiary alcohols for that reason. And just a note about that terminology, we classify the alcohols based on the carbon they're attached. So in ethanol, the OH is attached to a primary carbon, so we call it a primary. That's a tertiary carbon. It's got the tertiary alcohol. The alcohols themselves aren't attached to more carbons because they're always just only attached to a single carbon. So we just use the carbon they're attached to. All right, so let's practice. What happens when we deprotonate these things?
I mean, the first one is the thoughts.
Okay. For all of them.
Oh, yeah.
So this is a different alkali earth metal, but it works the same way. So it's going to happen a lot slower, but also more safely in a lot of ways. We don't really use potassium because it reacts too much. If you remember thinking back to lab where we threw sodium metal and potassium metal into water, sodium metal was clearly unstable, caught on fire, maybe exploded. The potassium metal, like instantly, you threw it in water and it's right away popped. So we don't really use potassium metal. Lithium metal will work, and it's just, in fact, it's much safer, but it's just slower. And so either sodium metal, sodium hydride, or just lithium metal. So for this bottom part, I give you two choices. How do we determine what's most significant? Yes, let me reiterate. These are in order of most importance.
Okay.
So the most important thing is resonance. Then it's, do we have any electron withdrawing groups nearby? And then we start worrying about solvents and sterics. So for A, is there any resonance? No resonance. Are there any electron withdrawing groups near the alcohol? No. So all that matters then is sterics, that solvents.
The one on the left that have better.
Correct. So primary is going to be more acidic than a tertiary.
one on the left has the only groups.
Has all the electron withdrawing groups, right? Has all the electronegativity.
I was actually wondering about that, because on the exam, there was one of these, when it's like that, where it's like, just, let's say it's just the two that are.
So this is neither. It's not secondary. Because it's attached to a benzene, because benzene rings are their own thing.
Okay, but what if it wasn't? Would it be tertiary or secondary?
So what do you mean? What is it, like this?
Like without the alcohol, just what's with, like where you attach.
Oh,
Is that?
you could call that secondary, but really vanillic is a better option.
Okay,
Because they behave differently. We typically use primary, secondary, tertiary, quaternary for sp3 carbons. If it's not an sp3 carbon, we don't typically use that terminology. And even this one, this is the sp3. Technically, you could call it primary, but even better be allylic.
okay.
When in doubt, just use the right. Okay. Say that again.
Receivers, technical residence and work is in the ring those. Yes.
Correct.
But there's one other thing. Is there the, would that be considered for drive through the option?
You could think of it that way, but even more so, you get extra resonance.
And so it has like even more.
Yeah, because you have another pi bond attached to something that already has resonance, we get extra resonance. So for both reasons, and actually when we start talking about aromatics in more detail, we'll talk about this, but anytime you got a pi bond adjacent, that is considered a strongly electron withdrawing group. Because the resonance. So if it's electron withdrawing and gets extra resonance, that means it's easier to take that electron. So you were on the right track with that one. So it's more acidic.
And the one on the right has rearrangement, whereas the other one on the left.
Resonance, not rearrangement.
Resonance.
Right, because rearrangement means we actually move the same bonds. Resonance is just pi bonds and one pair of split bonds. Yeah, these, as long as you can remember
So then it would be.
these. Yeah, the one with resonance would be more acidic. These variables in this order, resonance is most important, electron withdrawing is second most important. And then you start looking at solvents. All right, couple more slides. This is review. If we want to make alcohols, we have several different ways to do that. Right, we had acid catalyzed hydration, we have oxymercuration, demercuration, we have hydroboration oxidation. We can label these with more details too. We can say Markovnikov with rearrangement. Mark, no rearrangement. And anti-mark. And so we have our standard hydration reactions are still gonna be our number one way of making alcohols. There are a few other ways to think about making alcohols though. And this is one of the biggest concepts from this chapter is this idea of oxidation states. So let's review redox for a second. So far we've been talking about formal charge. Right, we look at how many electrons are owned, minus how many electrons has the periodic table. So we can do things like we have an oxygen like that, we know it's going to have a -1 charge because it owns 7 electrons here and it only has 6 on the periodic table. Right, that's the way we've been talking about charge. Oxidation state is basically like splitting hairs version of talking about charge. With oxidation state, we're not talking about anything having a real charge. We can talk about it in terms of like electronegativity, basically. So oxidation state basically is a way of thinking about bonds. We treat all the bonds like they're ionic. And so it always is just going to come down to what's more electronegative. And we're still going to compare it to the periodic table. So the oxidation state in methanol, just in its regular Lewis dot structure, there is no charge. We can look at this and say, well, there's like a partial charge because the oxygen is more electronegative, right? So oxidation state is just basically zooming in on that. Say, okay, well, I'm going to treat this polar bond like the oxygen actually gets all of the electrons because it's more electronegative than the carbon. But then this carbon is more electronegative than the hydrogens. So we basically just say, okay, well, the carbon doesn't get those electrons, but it does get all 6 of those. So if it has 6 electrons, and on the periodic table it only had 4, the oxidation state on that carbon is a -2. It doesn't really have a -2 charge. This is just a way to think about how electron rich it is.
And why don't we want to go there?
Because the oxygen is more electronegative than the carbon, so the oxygen, just treat it like the oxygen's not going to share at all.
And then it would still the ones from the nice.
But it does get to keep the electrons from hydrogens because it's more electronegative than hydrogens. So the oxidation state on hydrogens is +1 for all of these. Right? Oxidation state on the carbon is going to be -2. The oxidation state on the oxygen is also going to be -2, which makes it super stable, right? Because oxygen, when it's got a -2 charge, that if we're just looking at the periodic table, it needed to gain 2 electrons to be stable, right? So when atoms have the same oxidation state that they would have as their overall charge as an ion, that usually means that they're stable. Right, so oxygen is much more stable as with an oxidation state of -2 than it is as peroxide. Because what do we do when we have something that is between 2 of the same element?
Should we split it?
Yeah. So basically, think about it that way.
Yeah.
And now this oxygen it gets to keep all of those. So 2, 4, 6, 7 electrons.
+1.
-1. So remember, electrons are negative. So it has one extra electron. That's not the same as it is when it's neutral, and it's also not the same as it is when it's really stable, which is a -2. So peroxides are super reactive because the oxygen is oxidation state of -1. And we really only see that with oxygen when it's oxygen attached to another oxygen.
Well, like, and I mean, I don't think it's ever like actually like an oxygen and together.
So you would go to, no, it does happen. I'm teaching polyatomic ions to my Chem 100 students right now. ClO3 with a -1 charge. Chloride.
Okay.
And if we draw this Lewis dot structure, we're gonna get
And
I think that's the right number of electrons. Basically, you can do this, but the oxygen is more electronegative than chlorine. I'm doing this from memory off the top of my head, trying to do it fast without stopping and count all the valence electrons. So I'm going to erase it because I'm not sure I drew it right. But yes, you can have oxygen attached to chlorine.
you would give option.
And you would give the electron scales. The oxygen down electronegativity of 3.5 and chlorine is 3.0.
Okay.
So basically, the only thing more electronegative than oxygen is chlorine.
So we're not looking there, you're going to, they know it's
Right. I need to get Mariola to order in one of those pull down ones because I think that would be effective. All right. So what does this mean for carbons in organic chemistry? Basically, we can rank how stable carbons are based on their oxidation state. And we kind of group different functional groups based on the oxidation state of the carbon. So that now that we're in organic chemistry and we're dealing with larger molecules, we'll talk about each carbon is having a different oxidation state.
Okay.
If we have a system like, so this is all for a single carbon system. A carbon surrounded completely by hydrogens, you get a -4 charge. Oxidation state. Methanol is -2. Formaldehyde is a 0. Formic acid is a +2. And then fully oxidized carbon is CO2. So this is one of the reasons that carbon is super, I don't want to say useful because that's not really the right word, because that implies someone planned it. But one of the reasons it's so versatile and why it can exist in so many different states on Earth is because all of these are relatively stable oxidation states. Compare that to our transition metals where you might have 2 or 3 oxidation states that are stable, or oxygen really only has 1 oxidation state where it's stable, and that's when it's -2. So carbon, because it can have all of these, and it can also have in between these, we looked at like acetate. If we actually started assigning electrons here, this carbon gets 2, 4, 6, and then half of that. Right, so it gives it an overall 7 electrons, that gives it a -3 oxidation state. This one, this carbon doesn't get any of those electrons or any of those electrons. It does get one of those. So that is 1 electron, and it had 4 on the periodic table.
Yeah.
So you can get these odd numbers in between here when you start looking at larger molecules, because every carbon will have its own oxidation state. And that's why we really can't dig deep into oxidation state of carbon until you get to OChem. Because if I try to explain this to the Gen Chem students that are just learning this, and they want to treat acetate like C2H6 or C2H3O2, then they're trying to treat both of the carbons like they're the same charge. They're not the same charge. All right, so why do we use this? Last slide. I know we're out of time. If the oxidation state changes, then it's a redox reaction. So far we haven't talked about any of our organic reactions in the context of being redox reactions or not. We just look at them as just nucleophilic addition or things like that. But it turns out this is one of the ways that you can actually make an alcohol is by starting from an acid and reducing the carbon. Because the carbon here, we just did this molecule. This carbon is a +3. That carbon, you might have to draw out all of the bonds. It gets none of those, but it gets 2, 4, and it gets one of those, so it's got 5 electrons. So if we went from a +3 to a -1, we reduced that carbon. And so then the easiest way to think about this is if you add carbon-oxygen bonds, you oxidized it. That's actually where the term oxidized comes from. We use that word because oxidized means you added oxygen to something because oxygen is so electronegative. If it goes the other way, if you took away carbon-oxygen bonds, then it's reduced.
So we're gonna have oxidation reactions and redox reactions.
Reduction. So since this is OChem, we're usually thinking from the point of view of the carbon, where we'll talk about it like, okay, well, this is an oxidation reaction. It had to also have something else had to be reduced for that to happen. But we're talking about it from the point of view of the carbon. So we'd say that the carbon is oxidized or the carbon is reduced. Or in this case, neither. Because the carbon here, it doesn't get either of those 2 electrons, it gets 1 electron there, 1 electron there. So that means it's a +2 charge. We didn't change either of these. So it's still +1 or an electron there and an electron there. And you don't get either of the chlorine electrons. So it's still a +2. It's definitely a reaction that happens, but it's not a redox reaction. So this is our case of neither. The carbon could be oxidized, it can be reduced, or it can be neither. It's right up there. Right? We wouldn't say that they didn't react.
Because it did.
Because it did. It's not the same compound it was when it started, but it didn't get oxidized or reduced. And that's going to be sort of our really broad way of classifying reactions that involve oxygens. Is it a redox reaction or is it I don't want to use the term rearrangements because we already used that. But a restructuring without changing the oxidation state.
And what were the oxidations to the number of the middle? We should the oxidized and reduced, what were the?
So here we did this one on this side. So it doesn't get any of those electrons, it doesn't get any of those electrons, and it gets one electron there. So if that's one electron and it started with 4 on the periodic table. So exactly. Versus this one, you get 1 electron from the carbon side, none from the oxygen side. So it has 3 electrons. So it went from a +1 to a +3. So that makes sense. All right. Obviously, we only had about half of one lecture this week.
Yeah.
So the quiz this weekend will be light. Basically, it's practice with this. How much snow did you remote?
Measure it.
Oh man, I had 3 driveways I was taking care of because we had a neighbor that I mentioned, and my parents are out of town too. So, and then they had the full on 4 feet tall, 8 feet wide berm because nobody had been clearing their driveway for all of Tuesday.
Yep.
So at least we got a plow one. I was very surprised that we got a plow Tuesday night.
Yeah, we got one at 2 a.m. on
Yeah.
Tuesday. Well, I guess
So-
on Wednesday at that point, but
Yeah.
Mikey was with us and he couldn't get it to work, and so, because we didn't get a plow, and we get like, I think we got probably like 5 feet that day, and so he was like, I'm not